Welcome. So in this video, we are going to be taking a look at the most current model of the atom, which is called the quantum mechanical model. Now, if you've heard anything about the quantum mechanical model of the atom before, or quantum mechanics, it's probably sounded like it is super hard, like it's impossible to understand. And I actually think when we start looking at the model of the atom that we get out of this theory, it's not totally incomprehensible. It is a little bit tricky, and there's some things in it that are definitely weird, but I think we can understand this well enough at our level so that we can really get a good grasp about the atom, the way it works, the periodic table, and ultimately like bonding and the ways that atoms combine together. This whole theory is really based around a central idea, and that central idea has to do with what we call quanta. So when we actually talk about quantum mechanics, what we're talking about is a finite amount of energy, and then basically electrons always have one specific amount of energy, and they can actually like gain or lose some energy, but they can only really exist at exact energies. So I think the best way to illustrate this is using a model that we've actually already worked with, and that is called the Bohr model of the atom. So let's take a look at a Bohr model of an atom. It looks something like this, right? It has the nucleus in the center with the protons and neutrons, and then the electrons exist at specific energies, or in other words, at specific quanta. So we learned that electrons, you can have two of them on this particular orbital, the first orbital around the nucleus, and then you can have 8 electrons in your next orbital around the nucleus, and then another 8, and then you never did any more because it doesn't really work after that. But you end up basically with a structure that looks something like this. Now, when we say quantum, what we're really saying is that electrons have to be on the line. Electrons are not allowed to exist past or inside of the line. They cannot be found there. They can only be found at specific energies. And when we say energy, basically what we're talking about is a distance from the nucleus. So from there to there is one energy level. From here to my next orbital, well, that would be a different energy level. And then you even have another energy level that goes all the way out to there. And you may even have more that extend further on, depending on how many orbitals are really in that molecule. Now, we call it quantum mechanics because mechanics is about motion. And so really what we're talking about with quantum mechanics is the movement of electrons from one ring to the next. So I'm just gonna clean this up a little bit, and then we'll take a look at what's actually going on as these electrons move. So I need to rebuild my, my orbitals here. Okay, and what's really happening is we have our electron existing at the lowest energy it possibly can. And what's going to happen is it's going to intake some energy. And when that energy hits it, this electron now boosts the amount of energy that it has. So it can actually jump up to the next highest orbital. The only thing is electrons, I always say electrons are lazy. Electrons want to be at the lowest energy they possibly can. So this electron is actually going to jump back down. But in order to do that, it had to lose this much energy, the amount of energy from here to there. And that energy can't just like disappear, it has to go somewhere. And that energy is given off in the form of a photon, which is basically light. when these electrons jump down, they're giving off different amounts of light and at different energies. And we can actually like analyze this and look at the energy, which is related to the color. And so we can actually get electrons being given off by atoms because they jump up and jump back down. So a really good example of this would be, think about like street lights in the city. You see orange lights most of the time, and that's because they're filled with sodium. What's happening is electricity is flowing into that sodium. The electrons in the sodium jump up and then jump back down. And as they jump back down to a lower energy level, they give off orange colored light. And that's just like a characteristic of sodium. Sodium always gives off orange light if you end up putting enough energy into it. So that's kind of the basic idea of quantum mechanics, is that electrons jump from one orbital to the next. But there became a real twist in this whole thing when somebody discovered what we call the uncertainty principle. So the uncertainty principle is this. It's that you cannot know the position and momentum of an electron at the same time. Now, this idea is probably a little bit more precisely stated, that the more precisely you know the position of an electron, the less precisely you know its momentum. This all has to do with the fact that electrons are actually waves. And so as we think about an electron, we kind of want to think about it as a wave at this point. So let's think about how we would know the momentum carried by a wave. Well, in order to do that, you actually need to like sample a fairly large stretch of the wave in order to get an idea about how much energy or momentum it's actually, like how much momentum it's actually carrying. So you need to take like a greater portion of it to find that out. But as soon as you take a greater portion, let's think for a second, like, where is the wave? What's the position of that wave? Is it up here? Is it down here? Is it the entire thing? Well, if that's our problem, then maybe let's think about narrowing this view a little bit, and let's just pick a really small section of it. But as soon as you take a small section of that wave, you now know much less precisely the momentum of it. And so this is ultimately a problem to do with the fact that electrons themselves are waves. So this whole idea led us to what we call the uncertainty principle, the fact that we can't really know the position and the momentum of the wave really well at the same time. So if this is the case, then how do we actually deal with electrons? Well, it came to using something that's called probability. So really like looking at the statistics of it. And so this is what we did. And now we use what are called electron clouds, or probabilities of where electrons tend to spend most of their time. So if you look at this diagram here, it shows you a nucleus in the center. You'll notice there's a whole like dense area around it. Well, that means you're probably going to find electrons like in this area. You'll notice there's also a little bit denser spot around here because you're probably going to find electrons there. Now keep in mind, this is a three-dimensional model, so it looks like you're seeing things in between, but really this is kind of like it's a big sphere surrounding it. And so this is really what quantum mechanics deals with, is it deals with the probability of where we would find electrons. And what we do in quantum mechanics is try to describe the distance from the nucleus and the shape that those electron clouds would take. Now, we describe those distances and those shapes using some sets of what are called quantum numbers. And those quantum numbers really come in four different varieties. There is what is called the principal quantum number. And that is the distance from the nucleus. And so what you're going to see is when we are dealing with quantum numbers is sometimes a quantum number might actually look like 1s2. And I know that seems super weird right now, but the principal quantum number would be like this. That's really telling me if my principal quantum number is 1, then it's the closest electron cloud to the nucleus. Let's say there was like a 2s, and I know we're looking at like s's and things like that, but really the 2 here would be the quantum number, and the principal quantum number, and it's telling me that this would be like the second distance from the nucleus. And so that's what the principal quantum number is. It is the distance from the nucleus in that particular atom. Now, there's another quantum number that is called the angular quantum number. And I always think this is like the weirdest one because it's not actually a number, it's a letter. And it tells us the shape of the electron cloud. So is it like a sphere? Is it kind of like a balloon shape? Like what does it actually look like? And we represent this with letters, S's, P's, D's, and F. And each of those letters means one specific shape. So in here, I wrote S's. Those tell you the angular quantum number. This would tell me, like we'll learn this later, that this would be a sphere. You may be thinking like, oh, what would go with P? S is the only one that actually relates to the actual shape. P, D, and F are just like letters that we ended up using. There is what's called the magnetic quantum number. And the magnetic quantum number has to do with the orientation in space. And so we're talking about a three-dimensional world. And so you have to think along like the y-axis, the x-axis, and since we exist in 3 dimensions, okay, you got to pretend that this is like popping out of the board at you and going into the board away from us. This is what's called the z-axis. And so the magnetic quantum number tells you really which of these axes does it lie on compared to others. And then the last number is what's called the spin number, the spin quantum number. This is kind of complicated. Let's just pretend it really represents the direction of the spin, but it has more to do with the way the wave is working. We're going to call it the direction of spin of electrons. Okay, that's not actually what it is, but it's like an easier way to think about it right now. And so that is ultimately what those different quantum numbers are going to stand for. And what we're going to do is work through what the different quantum numbers can look like for a different element. So I'm just going to clean this up, and then we're going to take a look at those different shapes and what they actually mean. So I mentioned that there are those angular quantum numbers. Those angular quantum numbers represent the shape that element's electrons can be found in. And the first of the shapes is what is called the S shape. And these are called subshells. So the S subshell is just a sphere. So what it means is that you would have your nucleus in the center, and then surrounding it would be a sphere of electrons. There is only one sphere, or S subshell at every energy level. And what I mean by energy level is distance from the nucleus. So that's really what we're talking about when we say energy level, is a distance from the nucleus. Now, each S shape can hold 2 electrons. So we can hold a maximum of 2 electrons. That is the lowest energy shell, is the S subshell. It first appears at the first energy level. Okay, so that is our S subshell. There is also what is called a P subshell. Now, the P subshell is often described as dumbbell shaped. And I like to think of them almost like you took 2 balloons and tied them together at the ends. So you kind of have a shape that looks like this, connected to a shape that looks like this. And this would be one of the P subshells. But because it has this shape, there's actually one of these that exists on the y-axis. There is one of these that exists on the x-axis. And there is one of these that exists on the z-axis. So it pops out, goes away on the z, which means there are 3 P subshells at each energy level. And it doesn't appear, so it first appears at the second energy level. It can also, each of these hold 2 electrons, which means it can hold a maximum of 6 electrons. So at most, it can hold 6 electrons. Now, I know this probably seems super confusing right now, and that's kind of the way that this goes. By the time we get to the end and look at some examples, it'll start to click together. It will actually start to fit together. But here's what I wanted you to think about. We often have thought about the atom as like this series of rings, when in reality, the atom is actually more like an onion. It's made of layers. So you have your nucleus at the center. And then the first energy level is the first distance from the nucleus. And that first distance from the nucleus only has a spherical shape around it, an S subshell. Then, at the next energy level, the next distance from the nucleus, there is actually also another S subshell, so another sphere. So this kind of starts to look like the Bohr model now. But the second energy level also has the p orbitals. And so along the y-axis, along the x-axis, and along the z-axis, there are different orbitals. And so the atom is more like a series of layers made up of these different shapes that overlap each other. Now those are two of the orbitals, the s and the p, but there are also other orbitals as well. Now the other orbitals are called the d and the f. So the d orbitals, they have quite large shapes because they become much larger. And there are actually 5 different shapes for each of those orbitals. And each of those shapes can hold a maximum of 2 electrons, which means a maximum of 10 electrons in the d shell. The f shell, on the other hand, has even bigger shapes. So it has up to 7 shapes at the f level. And each of those can hold a maximum of 2 electrons. So 7 shapes, 2 electrons per orbital. That means a maximum of 14 electrons at each energy level. And so this little diagram here, this little chart kind of sums everything up. The S shell shows up for the first time at the first energy level. And there is only one of these shapes per energy level, meaning there's a maximum of 6 electrons. The P shapes show up for the first time at the second energy level. The second energy level also has 3 shapes, 3 P shapes at that energy level for a maximum of 6 electrons. D doesn't show up for the first time until the third energy level. There's 5 shapes for a max of 10 electrons, and the F orbitals don't show up for the first time until the fourth energy level. There are 7 shapes for a maximum of 14 electrons held in that orbital. So what does this all really mean? Like, really, we're just kind of talking about words, but maybe we should go through an example and talk about what does this actually look like when we draw out an atom. So to draw this out, here's what I wanted to do is I wanted to work through an example of what is called orbital notation. And in orbital notation, we try to describe all of the quantum numbers as best we can for one element. Now, here's the weird thing. When I say draw the atom, remember the Bohr model? It actually looked like a picture. Here it's actually going to look like a bunch of letters and lines and arrows because we're going to represent the electrons as arrows. They're either going to point up or they're going to point down. Okay, so we're going to work through an example of nitrogen. And to work through this example, what we want to do is figure out how many electrons in total does nitrogen have. It has 7 total electrons. So the way that we do this is we always start with the lowest energy level. This idea of starting with the lowest energy level is based on a rule called the Aufbau Principle. So the Aufbau Principle is that we always start with the lowest energy subshells very first. And the lowest energy subshell is the 1s subshell. And what I'm going to do is make a little line and I'm going to write on that line. But 1, because 1 is the principal quantum number, meaning it is the distance from the nucleus. So principal quantum number. And then S is the shape that it takes, the angular quantum number. Now, if you want to know, how did I know that it was 1s? Well, I'll show you a little trick over here. There's a way that you can remember this, and then I'll show you later on how you never have to use this. But I'm going to make a list of all of the possible s orbitals. They start at the first energy level, and they work their way up. And there are in total 7 energy levels. And then I'm going to make a list of all the p energy levels, and they start at the second energy level. So 3p, 4p, 5p, 6p, oh, I forgot, 6s, 7s, 7p. Okay, then we're going to start a list of the d orbitals. And the d's don't start until the third energy level, so the third distance from the nucleus. And then I'll make a list of all the f orbitals, and they don't start until the fourth energy level. And actually, we don't even need 6f because there is no 6f and there is no 7d. Okay, so there we go. Now, the way that we figure out the order using this chart is we draw diagonal lines. And whatever we draw a diagonal through, that's what comes first. So the first energy level is 1s. And then the next one is 2s. And then the next one is 2p. And then 3s. So 2p followed by 3s. And then 3p, 4s. 3d, 4p, 5s. 4d, 5p, 6s. 4f, 5d, 6p, 7s. 5f, 6d, 7p. And that's how one way that you can learn the order that the orbitals go in, and make sure you follow the Aufbau Principle. Now, we can also next fill this with electrons. So what we're going to do is we're going to draw electrons as arrows, and we have to make sure those arrows point in opposite directions. Why? Well, that's another rule, which is called the Pauli exclusion principle. Every subshell can hold a maximum of 2 electrons, but they have to spin in opposite ways. So that's why I've done this. Now what we're going to do is this orbital is full, and I still have 5 electrons left. So I am going to add another orbital, and I use the next highest energy level. So I've already used 1s, so now I'm going to move on to 2s. 2s has 2 electrons in it. I still have 3 electrons left. So now I go to my next orbital. So I go to the 2p. Now there are 3 shapes for every energy level with the p. So p shows up for the first time at the second energy levels, second distance from the nucleus. And it has 3 shapes. So what that means is we are going to draw 3 lines like this. We have 3 electrons left. So the way that we're going to add them is we're going to go 1 here, and then we have to make sure there is 1 on each of those subshells before we pair any up. You may be asking why. Well, it's another rule, and it's called Hund's rule. And Hund's rule is that when you're filling those shells that have more than 1 shape at an energy level, you have to put 1 in each before you can pair them up in 1 shape. And so that's why I did this the way that I did this. Okay, so now we have our orbital notation for nitrogen. So you may be wondering, like, what does that even mean? Well, to figure out what this means, I'm going to show you something that I'll never really ask you to do because it would be cruel to make you have to try and do this. But I want to show you essentially what does nitrogen look like. And I'll show you as best as I can in this diagram. So you have your nucleus with your protons and your neutrons in the center. And then in the first energy level, you have a sphere, that's the S, that holds 2 electrons, each spinning in opposite directions. But then at a second distance from the nucleus, you have another sphere. That sphere holds 2 electrons that are paired up with each other. And I'm going to write it over here. But also at the same distance from the nucleus, you have 3 different shapes, one on the y-axis, one on the x-axis, and one on the z-axis. And each of those holds a single electron. So this molecule has essentially, this atom essentially kind of has electrons that look like that. I know that's super weird, but that's kind of what it looks like. I'll never ask you to draw this over here. I would ask you to be able to draw the orbital notation. Now you may be wondering, like, why do we need to know this? Like, what's the advantage of this? Well, this actually shows you a ton of information. We just don't know it yet. The valence shell is the highest energy orbital, or the furthest distance from the nucleus that holds electrons. It is the part that holds the highest principal quantum number. So let's count how many electrons are valence electrons in nitrogen. There's 1, 2, 3, 4, 5. And what do we know about those valence electrons? Well, 2 of them are paired up and 3 of them are unpaired. Hopefully that sounds familiar, because when we drew the Lewis diagram, there were 2 paired up electrons and 3 unpaired. There's also some other information that we can glean from the periodic table. So let's look at the periodic table and let's find nitrogen. Nitrogen's highest energy electrons are in the 2nd energy level. And what row is it in on the periodic table? It's in the 2nd row. The 2nd row is the 2nd energy level. The principal quantum number is the row on the periodic table. That's actually what it means. The other thing we notice, the first energy level of every element at every energy level is the s orbital, which holds 1, 2 electrons. 1, and then at the 3rd energy level, 1, 2 electrons. 1, 2 electrons. 1, 2 electrons. The p's hold 1, 2, 3, 4, 5, and 6. The d's hold 10. So from here to there. And the f's hold 14. So from here to there. There's actually blocks on the periodic table that represent the different shapes of the electrons that you would find as valence electrons. So the first 2 columns in the periodic table are called the s block because their valence electrons are filling the s shell. The p block, they're filling their valence electrons into the p orbitals, d orbitals, and f orbitals. I do want to point out something really important here though. The 3d orbital actually starts here, even though it's in the 4th row of the periodic table. And that's because 3d is actually slightly closer to the nucleus than the 4s. And the 4f actually fits right there after the 6s. You see, the periodic table is actually meant to look like that with the lanthanides and actinides. The 2 bottom rows that seem disconnected, they're actually meant to be right there. But this doesn't fit nicely on a sheet of 8.5 by 11 sheet of paper. So instead we drop them below and we pull this side over and we end up making your periodic table looking the way that it does. So this is why the periodic table really looks the way that it does and why it has the shape that it does and why elements fit in the place that they do. And the quantum mechanical model actually explains so much about how the elements actually behave and why they do the things that they do and why they are where they are on that periodic table. So let's do another example. Let's pick one that's a little bit higher on the periodic table. I'm going to pick bromine, so Br, and it has 35 electrons. So let's work our way through this example. So we are going to work with bromine, and we know it has 35 electrons. We always start with the lowest energy electron. That's the 1s orbital. It can hold a maximum of 2 electrons. After 1s is 2s. S's have one shape per energy level and hold a maximum of 2 electrons. After 2s comes 2p. P's hold 3 shapes per energy level, and there are 1, 2, 3, 4, 5, 6 electrons maximum into that p shape. I want to jump back to the periodic table for a second. You notice 1s, 2 electrons, and I mentioned that in the periodic table, if we take a look at that periodic table, the first ring, well, that first ring has 2 elements, 1, 2, both with electrons in the s orbital. Next is the 2p. Let's load this up so that you can still see it. Oh, you know what, that's not going to work. So next is the 2s followed by 2p. So let's look at our periodic table. 2, well, that's the second energy level. S is the first part here. 2p starts here. There are 6 here. What's going to come next? Well, 3s followed by 3p. So let's do that. 3s comes next. S's hold a maximum of 2. P comes after S, so 3p. It's a p, so it has 3 energy levels. So 1, 2, 3, 4, 5, 6. We still have to keep going because we're not finished yet. We still have extra electrons to go. So what's going to come next? Well, look at your periodic table. After you get to the end of 3p, we go to the next part of the periodic table, which is the 4s. So we're at 4s next. S's can hold a maximum of 2. So what comes next? Well, remember I mentioned 3d is actually what starts here. So we're at a d orbital, but the d's are always one behind the s's. So now we have 3d. And because it's a d, remember there's 5 shapes per energy level. So that means 1, 2, 3, 4, 5 lines. Each of those holding a maximum of 2, which means a d orbital can hold up to 10. What comes next? Okay, look at your periodic table. After the d orbitals are over, we're at p orbitals, and in the 4th row, so 4p. And a p orbital has 3 shapes. Now, I can tell you, I haven't even counted yet. I'm going to put 5 electrons in here. How do I know that? Because of the periodic table. Look at where bromine is. That's what we're trying to draw. It is 1, 2, 3, 4, 5 elements into the 4p orbital, which means that if I count this up, I should have 30 electrons right now. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 31, 32, 33, 34, 35. That's why I don't need the chart of 1s, 2s with all the arrows. My chart is the periodic table. So what this means is I should be able to pick an example from anywhere on the periodic table and actually predict where I'm going to end. So let's do that. I have not rehearsed this in any way. We're just going to do MO, molybdenum. It has 42 electrons. So by the time that I finish drawing molybdenum, I know it should end with 4d4. 4 electrons in the d orbital. So 4 electrons in the 4d. Why do I know that? Well, this is the 5th energy level, so 5s. And remember, the d's are always one behind the s's. So this is 4d, 4d with 1 electron, 4d with 2 electrons, 4d with 3 electrons, 4d with 4 electrons. So let's try it out. Molybdenum has 42 electrons. And let's write down my prediction. My prediction was that we end with 4d and 4 electrons in it. So let's try it out. What comes first? Lowest energy orbital, 1s, holds 2 electrons. 2s holds 2 electrons. 2p comes next. P orbitals have 3. So 1, 2, 3, 4, 5, 6. Then 3s. S's have 1 shape per energy level. Then 3p. P's have 3 shapes. Holds a max of 6. So now I've used 2, 4, 6, 8, 10, 12, 14, 16, 18. Next is 4s. Followed by 3d. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, at this point, I have used up 10, 12, 18, 20, 30 electrons. Next is the 4p orbital. So now I have used up 36 electrons. After 4p is 5s. So I've used up 38 electrons. I need 42. And after 5s comes 4d. D's have 5 shapes. I have 4 electrons left. 1, 2, 3, 4. 4d with 4 electrons. The periodic table actually helps us see these different orbitals and see these different shapes. And that's what's so great about the quantum mechanical model, is it actually explains to us so much about the ways that atoms work. And it helps us understand things like, why are certain numbers of electrons paired while others aren't, and why do atoms and molecules behave the way that they do. And as we work our way into bonding, we'll see that the number of bonds that form really is the unpaired electrons trying to match and find a pair somewhere. And so that's what we're going to be coming up with next, is taking a look at how do substances bond together. Make sure you practice this. Make sure you try it. The more you do this, the better it'll get. And hopefully it makes a little bit more sense now than when you first read through the notes and started looking at this idea. So thanks for watching, and I'll see you next time.